Have you ever wondered what life would be like on this planet if the magnetic field didn't exist? Earth's magnetic field, also known as the geomagnetic field, is a field that extends from the interiors of the Earth out into space. The relative movement between the inner core and the outer core create a geodynamo, which protects us from cosmic radiation like solar wind. And it's safe to say that life on this planet would not exist without it. And one thing you may not know about the magnetic field is throughout Earth's history, it has flipped many, many times. What were the consequences of this? How do we know they even flipped? And when was the last one? All of these questions are going to be answered in this episode. I'm your host, MrEarthGuy, and welcome to Earth SciShow. A geomagnetic reversal is a change in a planet's magnetic field such that the positions of magnetic north and magnetic south are interchanged. The Earth's field has altered between periods of normal polarity, in which the predominant direction of the field was the same as the present direction, and reverse polarity, in which it was the opposite. These periods are called crons. And reversal occurrences are statistically random. There have been around 183 reversals over the last 83 million years. On average, that equates to around 1 every 450,000 years. The last reversal occurred some 780,000 years ago, which technically means we're statistically due one any day. And you must be thinking, how quickly do these events occur? Well, there's general consensus that the average reversal is somewhere between 1,000 years to 7,000 years to complete. And like with most things in science, there is a scale of the reversibility. If it lasts for between 2,000 to 12,000 years, it's counted as a full reversal. Anything shorter, and it's just an excursion. However, there have been occasions where we've had a superchron, which is when polarity changed for nearly 10 million years. There are two well-established superchrons, the Cretaceous normal and the Kiamen. The Cretaceous normal lasted for almost 40 million years, from about 120 to 83 million years ago. The Kiamen reversal lasted nearly 50 million years in the late Carboniferous to the late Permian. This is some 312 to 262 million years ago. So how do we know that the poles have flipped to begin with? Well, for that, we look at the ferromagnetic properties in rocks. You see, most sedimentary rocks incorporate tiny amounts of iron-rich minerals, whose orientation is influenced by the ambient magnetic field at the time at which they were formed. These rocks can preserve a record of the field if it's not later erased by chemical, physical, or biological change. Similarly, the past record of geomagnetic reversals can also be observed in the sea floor. The ocean floor is created at ocean ridges, and the basaltic magma is usually rich in iron. These iron particles align themselves with the magnetic field at the time of creation. We call these magnetic stripe anomalies, and these were actually some of the first pieces of evidence to show that plate tectonics theory was in fact correct. This creates a magnetic barcode effect on the ocean floor. So what causes the geomagnetic field of the Earth to change? Well, we know that the Earth's magnetic field is generated from a geodynamo action, in which convection currents in the molten iron of the planet's core generate electric currents which in turn give rise to magnetic fields. These magnetic fields in the core are then amplified by the relative movement of the outer core. Today, we're still unsure why the polarity flips, but there are several hypotheses. Some scientists think that the geomagnetic reversals are not spontaneous processes, but rather are triggers by external events that directly disrupt the flow of the Earth's core. Proposals include impact events like meteorites or internal events such as the arrival of the continental slabs carried down by the mantle by the action of plate tectonics at subduction zones, or the initiation of new mantle plumes from the core mantle boundary. And even though more research is needed to try and find an exact cause, we still know they exist because the evidence is in the geological record. So we already know the last reversal was some 780,000 years ago, but when was the last excursion? If you recall, excursions are short-lived reversals. And to answer that question, we have to look at caves and trees. The last major excursion was called the Last Camp excursion, which happened around 42,000 years ago. Evidence for this was found in France after lava flows were found to contain bits of iron that were basically pointing the wrong direction. Volcanic activity back then, during the flip, produced this distinctive iron signature as the molten lava cooled and locked the iron into place. Iron molecules embedded in sediments around the world also captured a record of this magnetic wobble, which unfolded over about 1,000 years. So what do caves and trees have to do with the Last Camp excursion? Well, in some groundbreaking research, scientists were able to use well-preserved trees that were alive during the last camp excursion to pin down the precise timing of the event. And this new information has led them to link the flipping of the poles to key moments in the prehistoric record, like the sudden appearance of cave art and the mysterious extinction of large mammals and the Neanderthals. They argue that the weakening of the Earth's magnetic field would have briefly transformed the world by altering its climate and allowing far more ultraviolet light to pour in. For the research, the scientists used unusual trees from New Zealand called giant kauri trees. They can live for thousands of years and can end up well preserved in bogs. The trees themselves are quite unique, as they act like time capsules in a way that you don't really get to see anywhere else on the planet. Inside the trees that lived during the last magnetic flip, the researchers and their colleagues looked at the form of carbon created when cosmic rays hit the upper atmosphere. More of these rays come in when the magnetic field is weak, so levels of this carbon go up. The trees, with their calendar-like set of rings, took in this kind of carbon and laid it down as wood. That let the researchers see exactly when levels rose and peaked and then fell again. One tree in particular had a 1,700-year-old record that spanned the period of the greatest change. By creating a precise timeline, the research team was able to compare the magnetic field's weakening to other well-established timelines in the archaeological and climate records. They also turned to advanced climate modeling to try and understand how magnetic changes would have affected conditions on the planet. The ozone layer, for example, would have taken quite a beating. If you damage the ozone layer, you change the way in which the sun's heat actually impacts the planet. And as soon as that happens, the weather patterns change and the wind directions as well as heating goes AWOL. It basically goes all over the place. If the sun went through one of its periodic conniptions when the strength of the Earth's magnetic field was turned way down, a solar flare or storm would have sent a burst of radiation that could have had massive consequences for people living back then. And this is what they believe drove people into caves, as going outside would have increased the risk of exposure to radiation. And research like this is one step in the right direction for understanding whether reversals cause large-scale extinctions. If small excursions had the power to push people into caves, then what would the large ones do? Naturally, there has to be weakening of the Earth's magnetic field, and this has not always been the case through the record. Only time will tell, because technically we're 300,000 years overdue. And scientifically speaking, we have no idea what's going to happen next. That's all for this episode. I hope you enjoyed learning about the geomagnetic field and what polar reversals are, and more importantly, some of the unique ways that we're using to find evidence of these occurrences. And don't forget to hit that follow, it really helps the channel. Thank you for listening to Earth SciShow. I am your host, MrEarthGuy, and remember, stay curious.